Hello everyone, and welcome to the second SIPB Clue-Dump of the year. So for all those who don't know, SIPB is an organization dedicated to promoting computing within the MIT community. We run a variety of services as well as educate the public, such as through things like this. SIPB Clue-Dumps are a series of lectures on a variety of computing topics, from the very esoteric to the very broad, from the things that can appreciate to things for the experts. If you have ever wanted to give a talk about your favorite computing topic in the community, just send us an email at cluedumps@mit.edu. Today, we have our special guest. Nathan Foss is a member of MIT Class of 2020, studying math and computer science. And he's been a member of SIPB for how many years? For 3 years, during which he's worked on a variety of projects. And today he's going to tell us about the interplanetary future of the internet. Give it away for Nathan Foss.
Okay, so before I talk about IPFS, there are a few prerequisites that I need to make sure we're on the same page about. So if you feel like you understand sort of at a high level how like DNS and like packet switching and like the current internet works, like raise your hand. All right, so the brief overview of that is like the internet is made up of a bunch of like nodes, right? And there's each one has this address called its IP address, right? Which might be like 18 point whatever. If you're at MIT a year ago, and they send traffic to each other. So like when you look up something on the internet, it's like google.com or no, we'll use MIT.edu gets mapped to some IP address, 18.1.2.3, whatever, and then this, /foo gets mapped to this /foo. This is super scientific, sorry. That /foo, and then this part tells you like which computer to go to, right? So if I'm on this node, and I want to look up MIT.edu, I'll translate it with this arrow, which is DNS, and I'll talk about that in a second. And then my network, or my node, needs to know some way to send this traffic to this place. It's like a street address, but for one of these nodes. And so if this one happens to be 18.1.2.3, and I have a direct connection there, great. I can just send this request to here. This thing will either say, yes, I have /foo, and send it back, or it'll say, no, I don't have that. And like, great. But if there's no direct connection, then like somehow you still need to be able to get here. And generally the way that works is like, this node will be saying, oh, I have a route to anything that starts with 18, anything that starts with 18.1, anything that starts with like 74.3 or something like that, etc. And so when I at this node say, oh, I need to get 18.123, I'll know that this node has a route to 18.123, and it'll also tell me like how fast of a route it is essentially. So then I can send the packet, the request for this resource to this one. This one knows how to get to 18.123, so it will forward it, and that's how it goes. And if it doesn't for some reason, like if the packet gets dropped in the middle, like that's okay. It was designed to deal with that. You would wait a little while, and if you didn't get a response, then you would try again, maybe with a different route, over here or something, to a slower route, but one that works better. And like this node could disappear entirely, and you would keep sending traffic this way for a little while, and then you'd realize something was wrong, and you'd send traffic the longer way. And so like that's great. It's reliable. Things that it's reliable to participants dropping out of the network and coming into the network, and packets getting lost and out of order and stuff like that, because of this infrastructure that we've built up. But ultimately, what it is you have this address, and you need to get some packet there and back to get whatever it is that you're looking for. So this is how it goes. This part is DNS. the domain name service. And what this is a series of lookups. So in sort of a separate system, if you want to know what mit.edu maps to, then you would ask the .edu server, like, hey, do you know who MIT is? So, well, actually, sorry. First, you would ask the dot server. You would say, dot server, do you know edu, question mark. And the dot server would say, yes, it's, you know, some IP address 1234, or 1243, maybe. So it's some IP address, and then you would say, okay, great. Check this IP address, and ask it, hey, .edu server, do you know MIT? And then this .edu server would say, oh yes, you know, that's 18, can't draw 18.123, and then you'd say, great, that's what I was looking for, and you plug it in here and send off your request, and hopefully it gets to this node. It's a lot more complicated than that, but like that's really the core principles of how it goes. Okay, great. So that's the current internet, and as you may have noticed, it works pretty well. But there are some things that we could improve. So, for example, connection speeds are getting faster, right? Like pure megabits per second is going up, but the problem is that the connection speeds aren't going up as fast as the data that we're producing is going up. So, you know, we have over time, the amount of data that we're producing, like our pictures get bigger and we have more of them and stuff like that, right? This is going up pretty quickly, and bandwidth is going up like that, which is a problem because now, like, you know, before your photo archive was smaller and the bandwidth was lower. But you were down here, right? So this is your photo archive, you know, 10 years ago with your bandwidth that could handle it. But now, like, the photos are bigger and there's more of them, and the bandwidth hasn't increased proportionally. So it actually takes longer to download and upload your photo archive than it would have for, like, you know, an equally representative photo archive 10 years ago. So that's kind of an issue. And then the problem is that this happens at all of the links in between. So like, for example, if this were YouTube instead of MIT, and this were you, and you wanted to like download some video, right? Videos are also getting bigger, there are also more of them. And now you're downloading it over like this link, and then this link, and then this link, and like all of those links are having the same exact problem where like the data is bigger and the bandwidth is not as much. It's not keeping up as much. So it's sort of a problem at all of those places. And if for example, I wanted to share a video with all of you, then the way we would do it is, oh, I should label my graph here. This is data. This is, so if I wanted to share a video with all of you, I would probably upload it to YouTube because that's like a convenient place to put videos. So, you know, here we are. This is us in our room. You know, we're connected to, where is it? There's an access point somewhere here. You know, we're connected to some access point which can, you know, speak the language of IP addresses. Oh yeah, it's back there in the ceiling. Right, so that's connected to something else at MIT, which, you know, manages all of MIT's traffic, and that's connected to like probably some internet service provider like Comcast or whatever, and then that's connected like somewhere else, and then eventually it's connected to YouTube. So this is us. That's YouTube. There are all of these links in the middle, right? If I wanted to share a video with you, the way that I would do it is I would upload this video. It would go through all these links. It would go to YouTube, and then, you know, the 20 people in this room would all download it, right? You know, 20 big arrows would all like try to download it from YouTube and get it back to here. And that's kind of silly because I had a video right here, and I could have just given it to you, right? We're in the same room. There's no reason for all of this traffic to go all the way, you know, to some data center in the Midwest or something, right? This is clearly like there's some inefficiency here, and so that should bother us a little bit. And like the majority of traffic is this kind of traffic. It's like passing around static like blobs of data. So I mean, like think Netflix, right? Netflix is a lot of the traffic, and that's just that over and over again. You know, if you're watching the same Netflix show as someone else in your dorm, you're both downloading it from Netflix's servers, or I mean, realistically, it's cached somewhere in Boston because Netflix is smart. But still, like it leaves your dorm to get you that video when your friend might have it on their computer already. So that's sort of the speed issue. There's also this sort of resilience to perturbations, right? So small perturbations are fine. If a couple of nodes drop out, like whatever, you'll just route around them. If you like a wire gets cut or something and you lose some packets, like that's fine. We have protocols to deal with that, and you can handle it. But for large problems, for example, like entire network partitions, so like China, right, and their Great Firewall have like partitioned themselves off, and sort of like there isn't a way to route around that. There was a few years ago in Egypt, like one morning, everyone in Egypt woke up and they just didn't have internet anymore because the government had decided that they didn't want people to be able to use it to coordinate resistance and protests and stuff. And like natural disasters, right? If every time there's like a really big hurricane and it knocks out power for a couple days, well, your internet infrastructure needs that power to keep going. And even if you and your town could like have a generator or something that could keep communications running, like it doesn't matter because to use the internet, you have to have some connection to like the backbone and like the Google data center to send your messages. And so it's not, the current one is not like able to handle sort of those big partition level perturbations. And one of the reasons this is a problem, or one of the reason that this is a problem, is that we have this dependence on the backbone of the internet. In order for me to send you a message, it has to go through Facebook servers, which are not here, for some reason. And like that's really inconvenient if there's a natural disaster and you can't reach Facebook servers, but we could potentially talk to each other and like coordinate something useful. Or if we're in China or whatever and like we can't reach Facebook servers because traffic to Facebook is just blocked. We should still be able to send each other messages, and we can, but we have to use WeChat instead, right? Which is the same problem but with a different name. So like the perfect example of when this doesn't make sense is if all of us wanted to collaborate on some document, right? We'd open up Google Docs, I'd share the link with everybody, we could all like get on this document and type or whatever. What's silly is that if MIT lost its connection to Comcast or something, right? And so we could no longer connect to Google's servers, then the people sitting in this room would not be able to collaborate on a Google Doc together. Which like there's no inherent reason that the stuff that we're typing has to go to the data center, to Google's data center, right? Like we could just be syncing updates between each other, and like the rest of the entire internet could be down, and as long as we're all connected to the access point back there, then we're all connected to each other, and we're good to go, right? There's no reason that we shouldn't be able to communicate on Google Docs, or couldn't collaborate on Google Docs, just like sitting in a room together, regardless of what's happening in the broader internet. And you could argue like, well, this is possible right now, right? People have made peer-to-peer Google Docs-like things that do have the properties that I'm talking about. So it's really the developers being lazy, right? Because the internet is always here and we're always like almost always connected to the data center, might as well just rely on that because it's easy, right? It's not it's not the internet's fault that things are like that. It's lazy developers. And like maybe, but the infrastructure sets what's easy and hard. So having peer-to-peer Google Docs is a lot harder than having the centralized Google Docs where there's a server that syncs everything. And part of the reasons are, we have NATs and stuff where like, networks are no longer sort of open. It's hard to connect directly from one peer to another. And this is like only getting worse. MIT just got a NAT and everything. So the infrastructure itself, like maybe initially would have been totally fine, but like the way that it's evolved has made peer-to-peer like a lot harder. And I mean, even while I was preparing this talk, I'm like typing up my notes in Dropbox paper for what I'm gonna say. And I'm sitting in my apartment in Central in Cambridge, right, which is like a wealthy place that has good internet, right? No reason that shouldn't work. And like my Wi-Fi was being iffy, and so Dropbox was like, okay, I can't do anything until you have like connection again. And I just sit in my own house with a hotspot, like typing up these notes, right? Because for some reason my Wi-Fi decided it didn't like want to work well that half hour. And like there's no reason that I shouldn't be able to just type notes into a document like on my own computer. It's not even being shared with anybody, right? That's kind of ridiculous. And so like the both of these scenarios with like the spotty Wi-Fi or the network partition or deliberate partitions or from natural disasters, ultimately what it comes down to is the situation where you have like high latency or low bandwidth or a lot of congestion, right? That's when it's like going to be hard to get a lot of traffic from one place to another. And so like IPFS is called the interplanetary file system because Mars is 3 to 22 minutes away, depending on the positioning and stuff, at the speed of light. So if we wanted to become interplanetary, there's no way that the current regime would work because the latencies are on the order of minutes, right? And so like that's kind of ridiculous because Elon Musk hasn't even made this big rocket that's going to take us to Mars or whatever. But it's a useful heuristic for these like high latency, low bandwidth, high congestion scenarios. And like there are a lot of remote areas on Earth that have high latencies measured in seconds or minutes. And like if they have any connection at all. Right? There are places in the United States, like rural United States, that has really terrible connectivity. Just because, I mean, if you're remote, it's like harder to run a wire all the way out there. Even inside Stata, right? Like the cell connectivity in Stata is terrible. Like this is the middle of MIT, right? This is not just a problem for like, people in remote places in the desert or something, right? This is like this happens to us regularly. And even if we were totally happy with like the current level of connectivity, it's just cheaper to use less bandwidth, right? So if all else fails, then at least you'd be using less bandwidth. And so the design paradigm that IPFS suggests we switch to is an offline first one, where like everything is designed to work offline. And then in the periods where you do have connectivity, you can sync up and like, have all the nice properties that you want from Google Docs where you can collaborate with people, et cetera, et cetera. But it should always be able to work offline. And if you can do that, then you'll be able to like very gracefully handle these high latency scenarios instead of just saying, sorry, you can't type anything in this document until you connect to Wi-Fi again, right? Okay, and then the last, well, not the last issue. There are more issues. Okay, so and then another issue of the current web is security, right? So HTTP is bad because people can just impersonate websites, and like if they if they manage to insert themselves in the middle, like get a free Wi-Fi in some coffee shop or something, and you connect through them, then they can serve you whatever the heck they want, and they can serve you your bank website and have you type in your login and everything, and like. You wouldn't know, right? So we have HTTPS to fix that, and that was really awesome. But you still need a certain latency to do like all the crypto handshakes and stuff that you need to. The certificate authorities themselves, like the security underlying HTTPS, those certificate authorities have been compromised in the past, and very may well be in the future. Like imagine if Let's Encrypt were compromised by some state-sponsored hacking group or something. It could do a lot of damage. It doesn't solve the problem where you can pretend to be a DNS server and like lie about what the website is, even if so you could prevent someone from connecting even if you can't impersonate who they're trying to connect to. And then of course it's still not ubiquitous, right? Like HTTP is still pretty widely used. Thankfully, the good bank websites have moved to HTTPS and stuff like that. And then it also reinforces the need for this backbone, right? Because with HTTPS, you're protecting the connection between you and the web server. You can't do nice things like cache the content close by easily, because you can't validate that, if that access point were caching, capital1.com or whatever, so that you didn't have to like do all the work to go to Capital One servers and like get the website. Like that would be really nice as the access point, right? But there's no way for you to verify that the access point isn't lying to you about what it is if it did do that. Not with HTTPS. And like there's some work on getting this to be possible, but it's not like here yet, and it's sort of like more of a band-aid than a permanent fix. Then also, like DNS is really easy to manipulate. You can just pretend to be a DNS server, and if people connect to you, then you can lie to them about anything, and they won't know until they try to connect via HTTPS and it fails. And then, yeah, so like end-to-end encryption is great, and we definitely want that, but it misses the point, which is that the data is what we want to protect. Yeah, question.
Is the band-aid DNSSEC or something else?
No, not DNSSEC.
What's the band-aid?
There's this cool thing, I think the Chrome team has been working on it, where you can like sign, you being a website can sort of like sign a piece of data to get cache, closer to the user or like in their browser or something, so that they can, so you can have the caching thing that I was talking about with the access point at capital1.com, and you could verify it because the cache data is signed by the person you're expecting to talk to. But I don't think that has been deployed or deployed widely. And right, it doesn't solve the other right problem. Right, so because this is sort of all missing the point, which is that you want to protect the data that's being passed around, not necessarily like the connection that you're distributing it on. And so that's one of the problems that I think that serves to solve. And then the last thing is just permanence. So links break all the time because the person hosting it stops paying for the web server because they don't want to, or because they change the structure of their website or anything, right? Like a small change can break a ton of links that had useful content at them and stuff like that. And the problem is that like this data is tied to the computers, which come online and offline all the time. And as soon as the one that was hosting something really valuable goes offline, tough luck, right? Unless you had the forethought to save, download everything beforehand or something like that. And like the problem here is that there's, this one person bears, well, I mean one computer, right, bears the entire burden of keeping some piece of content online, no matter how valuable it is to everyone else. So, if 1 million people get a lot of value out of this thing, but the person running the server isn't, serving ads or something to like get any value back, then you're like, why should they keep it online except for altruism? So that's another problem that I hope to solve. Okay, so now the main topic of today, IPFS, the Interplanetary File System. So IPFS was designed around these problems. And at its core, it is a hypermedia transport protocol, like HTTP. So it's all about like referring to and moving pieces of data around, like around the world, and that's like the core goal, which is the core goal of the internet. The key thing about IPFS that's different, and really like what gets you all of these nice properties that we would like to have, is a switch to content addressing instead of location addressing. So by location addressing, I mean when you say MIT.edu, sorry, this is HTTP, MIT.edu /foo/bar.jpg or something, right? This is some piece of content on the internet. This gets mapped to HTTP 18.123 /foo/bar.jpg. And then like you go to that thing and you get the piece of content that it gives you. IPFS wants to change this to /IPFS / and then like some hash. So this is, I'm making up random numbers. Oh, it wouldn't be a 0 because it's basically 2. making up random numbers here, but, and then foo / bar dot JPEG. Okay, so this is the big shift, right? We're going from the IP addresses, or yeah, to these hashes of content. And so this is really key, because now what you can do, if you, instead of asking for content by the location it's stored at, which may change or whatever, you can ask for the piece of content by the hash of the content itself, which never changes, no matter where it is, no matter what time of day it is, etc. And so that's really the key thing, where you can get it from anywhere, and then you can just validate what you got by hashing it. And if it doesn't match, then the person who gave it to you is a liar. And if it does match, then you're great, and you don't have to worry about it. So, for example, if I just downloaded, foo / bar.jpg or whatever, and I have it in this room already on my computer, and one of you wanted to download the same image, then I could just give it to you directly, rather than you going through this whole process of finding it somewhere else on the web, like in some data center in the Midwest or something like that, right? And that would be way faster, way more reliable, because the traffic never has to leave this room. It doesn't matter if the data center is on fire, I can just give it to you. And because I'm right here, I can give it to you much faster. So this is really the key, is this content addressing. Yeah.
Doesn't that also completely get rid of privacy? Because now the people in your room know what you're looking for?
Yes, I'll talk about that. Yeah, okay, so,
Question.
yeah.
Is the hash of bar.jpg the same as goo / bar.jpg, or?
No, so that's a good question, and I'm about to talk about that. This also, another good question is the hash is static, how do you figure out what the hash is in the first place, right? I only have to remember mit.edu and I can get whatever the most recent thing is from mit.edu. That's a great question, and I'll answer that after I answer that question. Okay, so how is this actually going to look? Is we're going to have a sort of hash-linked structure of sort of everything, right? So say I have a picture of a cat, right? So this is like some cat picture. We can call it cat.jpg or something. Or actually the name is not associated with the picture. So this is just some piece of data, right? This data has a hash. Maybe the hash is ZR3 whatever. And no matter no matter who has this picture, no matter where it is, whatever, it always hashes to the same thing. I'm glossing over the fact that maybe you want to use different hash functions, but that's solved separately. I can talk about that. For now, the hash is always the same, right? It's just it's just some binary data. It doesn't matter who has it. Okay, so this is a cat picture. I of course want to put it on my blog, because what else are blogs for? So, I make a new blog post, and this blog post has some text like my cat, whatever, my cat something, and then it has links to other content, right? So it has the hash of this cat picture, ZR3 whatever, and then it names that thing. So it decides to name it, cat.jpg. And this points to this content, because this hash is immutable. If you ask for this hash on the network, it always matches this picture, because we're assuming you're using a good hash function, so you can't make two pictures that hash to the same thing. If that's not true, then we're in big trouble, so I think that's an okay thing to assume. So my blog post has my cat, whatever, and then it has some link to this thing, which is embedded in the post. And then maybe this is linked on my blog website, which is going to have links to many sort of, it'll have links to this blog post, it'll have links to this blog post, it'll have links to this blog post, whatever. So the name of this cat picture, if you were just after the data itself, like the picture itself, then the name would be IPFS / ZR3 whatever, and that's it, right? That would get you the data for this cat picture. If you wanted to refer to the cat picture via my blog, then it would be up here. It would be /IPFS / the hash of this. So we'll say that the hash of this is maybe QM6 whatever. So this pointer right here would be QM6. So this would be IPFS QM6 / cat.jpg, because that's what we called it here. And if you looked up the hash of this thing, then you can just use normal names after that. But then if you wanted to go through the entire blog, which maybe this entire blog has a hash of h7p ... then you would say IPFS / h7p ... maybe it's named blog or something, or this could be blog post 7 blog 7 / cat.jpg. And the way that this gets resolved is you look up the thing that is this hash, which gives you this block. And then this block has some links to other things, and they have names. So the name for this link is blog 7, and it brings you to that hash. So then you look up this hash, and you get this blob of data, and you pick the next piece, cat.jpg. So whatever this piece says cat.jpg is, you look up that hash, ZR3 whatever, and you have your data right there. So if I wanted to send this picture to my friend separately, then I would just send them a message that says like, oh hey, look at my cat, and I would link just ZR3 whatever, right? Because they don't need to know about the whole blog thing, they just need a link to this piece of data. So that's great. And my friend likes this picture of my cat, right? Maybe they want to put it on their blog. So this is a blog 2, and it can have a pointer to this or whatever. And then the New York Times picks it up or whatever. So because this is a really grumpy cat or something like that. And so this is like something blogs whatever. And then it links to both of our blogs. So it says, it would link to this article. So it says, okay, it has a link to that blog. Like everybody's talking about this. Wow. And now you can access cat.jpg from if the hash of this is NR T or something, then you could get it through IPFS NRT ... I don't know what they call this one. They could call it the blog 1 whatever, not imaginative. Okay, so and then the first blog that they link to, and then that one knows cat.jpg. And then separately, if they really wanted to, they could embed the picture in their website and have a link all the way back here, which is also, it could be called kitty.jpg. So another valid path would be IPFS / the hash of this blob of data / kitty.jpg. And so the whole point of this is that if you went and read this New York Times post and you loaded this piece of data, so it showed up in the newsfeed, but then you were like, oh, these people look great, I'd like to read more about their blog, and you went here, and then this also loaded the piece of data. It's the exact same data, and you already have it, so you wouldn't have to download it twice, which is cool because even if the New York Times like copied this image, put it somewhere else, and like uploaded it themselves, it's still the exact same data, so it's gonna hash to the exact same thing. And these two really will refer to the same hash, regardless of like how many times they copied the data and moved it to a different computer and uploaded it at a different address, and then somebody downloaded it there and copied it somewhere else and then moved it somewhere and hashed it again. Still the same hash, still gonna be this piece of content. No matter which link you get it from, it's always going to be the same. So if you loaded all of these links, in order, you would only download it once, and that's pretty great because otherwise you'd be downloading it 5 times and it's the same data, so that would be kind of silly. Right. So this this sort of hash-linked data structure here is called the Merkle DAG. Merkle because it's hash-linked, and DAG because it's a directed acyclic graph. So I'll just write that down. So yeah, Merkle DAG is what that is, and that's sort of everything else in IPFS is sort of built around that and the nice things, the nice properties that it has. So some other examples of things which are Merkle DAGs, like blockchains are Merkle DAGs. They're just very boring ones because it's just a line of hash-linked things. But Git is a Merkle DAG, right? So every time you commit some update, what it does is it saves the delta in that commit, and then it points to the version that you're changing. So you don't have to, if you're working on a very large code base, you just point to the big blob of data that's mostly unchanged, and then you have this really small delta on top of that, which is awesome.
Yeah, that's not how Git works.
I mean, it's not.
That's how SVN works.
That's how Git works at the per file level,
Yeah.
not within a file. And it doesn't store diffs within a file.
Yeah. Right.
Except it does because of pack files. It's complicated.
Okay. Yeah.
The Git storage layer dedupes, not the Git tree of commits.
Yeah.
So my question, just to get my head around it, it seems like with HTTP, HTTPS, we're dealing with the application layer, for lack of a better term. But then below that is a transport layer, right?
Yes.
Is IPFS a transport layer, and are we keeping the underlying, because I don't see how, yeah.
Yeah. So the short answer is it's at a slightly different layer where it doesn't care, IPFS doesn't care how you like move the data. Like it could be, you would still use TCP to like move the data. So it's at a slightly higher layer. And I'll talk about the breakdown of the layers and stuff later on. But right, so back to Git, which is a very complicated system, and I just oversimplified drastically. But Git is still a hash-linked data structure. Oh yeah.
I have a different question about the last thing for you.
Oh yeah, sorry, go ahead.
Slide. What's the point of having names for these files if you're just going to include the hash in the name anyway? Like, why do you need 2 names for that file?
Yes, so this could be, well, there are like 2 ways to get to it, right? So this New York Times.
Isn't the third way to get to it just to stop it after the hash and not have any name after it? You said earlier that was it valid?
Oh yeah, so right.
Isn't that second path component there is the hash, right?
Yeah, these are all hashes. So the point of that is that there are many like globally valid names that will get you the same data. In this like static hash linked thing, you could get the hash of the actual thing. You could, this article refers to the hash of the thing. It also refers to something which refers to the hash of the
Is
thing.
that hash there the hash of the article?
Yeah,
Or the
so
hash of the content?
this is the hash of the article.
Okay, so
Which
that's
has a-
named in the article.
Yeah, which has a named pointer to the cat, and also has a named pointer to the blog, which has a named pointer to the cat.
Gotcha, that wasn't clear.
Yeah,
I thought
sorry
that
about
was
that.
just the hash of it.
Otherwise, it wouldn't be a Merkle thing.
Right. Okay, great. So, right, so yeah, Git uses this. This is one of the reasons that, sort of unlike SVN, you can work really nicely offline and then like sync things up later with the merges and stuff. And even merges, don't actually edit the Merkle DAG. They just add more to it on top, right? It's a new commit that references the old things, and like that's it. And so the dream of IPFS is that like all data is in the Merkle DAG and like represented in this way, which would be cool because then you can have all these like permanent immutable links. Versioning of everything would be easier, but mostly because of this like permanent links to not like data that can be duplicated, but doesn't have to be. Yeah. Okay, but of course, like the web is not static. Dynamic content is extremely important. How do you get these hashes in the first place is a very important question. And so like the Merkle DAG has to be static because it's hashes, you have to be able to hash the same thing to the same thing always. So the way that you would do dynamic content is you just keep a pointer at the Merkle DAG and you update the pointers. So Git does this with like branches and stuff, right? When you add a new commit, it like builds onto this Merkle DAG and then updates the pointer of master to like that new commit. And this is great, the Merkle DAG can do the Merkle DAG thing, and the dynamic piece is these pointers. But, I mean, how do you do pointers? Well, one way, and the way that IPFS currently does it, so this is not forced in IPFS. They like made an important distinction where the Merkle DAG is their core thing that like everything else is sort of, This is the key component that you really need. Everything else is optional and you can like do it in different ways. So for example, it doesn't matter to IPFS how you spread the Merkle DAG around, right? Like you could take it on a flash drive across some censored border and that is a totally valid transport. Or you could use like TCP or something. Like that's all fine, that can be swapped out, that can be upgraded, people can invent new things and then use that. Like, that'd be totally cool, and that's like a good feature. The current internet has this also, where like the only thing that really is sort of crucial to everything is the IP addressing. And then above that, you don't care how the content gets that IP address, right? You don't care about the routing. You can use different routing protocols if you want to. At the application layer, you don't even care how it's routed, like you just care that it gets there and gets back. Below that, you don't care if it's sent over like Wi-Fi or Bluetooth or like a wire or something. And this is the same way. The only thing that you absolutely need is this Merkle DAG. You don't care how it's spread. You don't care how applications don't have to care how it's spread or even how, whether you had it locally already or not. That's it. So this public key, so there's a way that IPFS currently does this, which is with public keys, does the pointers. And the way that this works is you have some public key, and this public key can sign records. So I'm going to go back up here because now I'm filling in this gap. Okay, so this is half the solution to the naming problem is you have IPNS, the Interplanetary Naming System, and then you have some ugly public key, whatever. And this is a pub key. And then that goes to foo/var .jpg. And this, you want the public key to map to some static hash. And that way you can update the static hash that it maps to, and you have this lightweight pointer thing. So the way that we're going to do that is with dynamic, with records associated with the public key. So IPFS has a record which is going to be a value, and this is some hash. For example, the New York Times one would be nrt ... It's going to have a sequence number, and this is so that you can tell which record to use if you look at 2. So this is to tell which record to use if you have 2. And then you have a signature. And this is signed by the public key associated with this record. So if you're the New York Times and you want to publish a new version of your website, then what you do is you hash the website with the new article about this cat or whatever. You create a new record with a higher sequence number, and then sign it with your public key. That, for now, we're assuming people know the New York Times public key. We'll get around that in a second. And then you disseminate that to the network. And everyone can see that this thing has been signed by the New York Times. Everyone can see that it's newer. Everyone can see the new pointer into the Merkle tag that you're supposed to be using. So that's great. Now we can have dynamic content. And the last piece, before we can have something as nice as mit.edu/foo/bar, is the human readable names. Again, this is something like with the current internet. You could have any number of systems for this, right? We currently use DNS. IPFS actually currently uses. A lot of people use it. Sorry, there's a variety of ways. A lot of people will do this through the Ethereum naming system, which is where you have some short name in the Ethereum naming system, and it maps to some public key, and then you update the public key. Some people will just do it through DNS, where you have a website and it maps to an IPNS public key, and then you can look up the record and stuff. So there are a variety of ways to get human readable names. It does not solve the problem of DNS insecurity if you use DNS, obviously. But I'm going to punt on that one because it's hard.
Quick question, is the signature there the same signature that you said was on the fix to the DNS earlier when I asked the question? Is that the same problem?
Are you talking about DNS?
You referred to this flaky fix of
Yeah.
DNS or whatever you called it, and you said it's based on a signature scheme. Is that the same problem in both cases?
No. So, well, if everyone used the signed cached versions in this way, then it would be kind of similar. But that's not applications aren't designed around thinking of content as a Merkle tag. It's designed around the location address.
I'm just saying the signature piece.
The signature piece. The problem with the thing that I was talking about is not verifying the signatures if you're using the, because that's all through the same certificate authority chain as HTTPS. The problem with that was both sort of updating and spreading it because of the infrastructure for that doesn't exist, and the fact that things are not built to be cached in this way. Okay, great. So now what's really awesome is that you don't need to rely on a specific person to even get dynamic content, right? You could just ask the network, hey, what's the most recent version for this public key? And people can send you all kinds of stuff. And if the signature doesn't check out, then they're lying to you. And if it does check out, then you have perfect confidence that what you're getting is true. And you have this mutable pointer into the Merkle tag, which is great. But now you haven't had to trust anyone, but it can still come from anywhere, which is
You have perfect confidence that it was true.
that it was true.
You have no way of knowing if it was the most recent version of that content.
Right. So someone could still deny you a more recent version if they control your entire, they could eclipse you and block all traffic that shows more recent versions.
The
That's
sequence number is part of the signature.
no, that's part of the record itself. So the signature.
You can't screw with the sequence number.
Right. So the signature is the signature of everything on
That's
here.
what I mean.
Yeah. Great. Okay. All right. So I'm gonna have to go faster through. Yeah. Okay. So that's the high level idea, and this gets us a lot of the properties that we wanted initially, of the like immutability, the connection thing, where if I have downloaded a video and you guys all ask for it, I can now just give it to you, and you're cool with that because you can hash it and verify that I'm not lying. We have the resilience where now, like, because you don't have to get to this very specific place in the internet, 8.1.2.3, it's okay if you get partitioned. You can still continue to like interact with the Merkle DAG and do everything, and you know, maybe there will be some content that you can't get because it's on the other side of the partition, but like the internet still works if it's partitioned, and there's sort of like if anyone on your side of the partition has this picture of the cat, then like everyone can, rather than you need to have a connection to the server that has the picture of the cat at all times if you want to be able to download it later, right? You know, because like with that, there's less dependence on the backbone. It helps drastically reduce the like latency and low bandwidth problem and the speed problem, because again, you know, the very worst case is if my blog is the only computer in the world that has this picture of my cat, right? And you still end up going all the way to the computer that's hosting my blog, get the data, and all the way back to wherever you are, right? That's like the very worst case, and that's how it currently is. In any other case, if anyone else in the entire world has this picture of the cat, you know, they could also serve it to you, and that would be better, right? Well, I mean, if they're closer, then it would be better. So that's really cool that like it's definitely an improvement, at least, you know, at a high level. And then again, it solves a lot of these security problems. Not all of them. With the human readable names, no one has a good solution for that besides blockchains, which like is probably not the best solution, but maybe. But past that, with this public key thing, with the immutable hashes that you can verify, you're putting much less trust on all the infrastructure in between. So that's great. I was planning to talk about how these things are implemented, but it's already been an hour, so I'm going to talk about them anyways if people want to stay and hear that. But this is a good closing point where like all of the big ideas have been put out there, and you sort of have a high level understanding of like why IPFS is exciting. Oh, and I should mention, this exists. It's implemented in Go and JavaScript at the moment. It has about 30,000 nodes online. At least it did during the summer. It might be more by now. And you should check it out. IPFS.io. You can build stuff on it. It's cool.
Thank you very much, Nate, for your excellent talk. So, reminder everyone to please subscribe to Cludumps-Announce to learn about all future Cludumps. If you want to teach a Cludump, please email cludumps@mit.edu. And please, please, please take some food. Take it home.
Okay, I'm going to keep talking now, but I won't be insulted if you leave because you know, it's only expected an hour. All right, so implementation. Okay, so the current...
Hey, Nate, how
Yeah.
much longer do you planning to go?
Hmm?
How much longer do you planning to go?
I don't know, half an hour?
Okay.
Okay, so like I said before, the current web has this stack of there's IP addresses in the middle, right? This is the one thing that you always have to use, no matter what. And then you know that can be over things like Ethernet. It can be over Wi-Fi. And then, you know, likewise, those things can be over fiber. It can be over, you know, satellite. It can be over, you know, any number of things, like you know, even radio, right? So this is all the ways that you could send traffic around. And then how to decide where to send traffic. There's like, the routing layer, which is, just BGP essentially. And then the how you handle packets that get lost or whatever, like what you actually send is, the TCP, sort of UDP, stuff like that there. And then what you're putting in those packets is, there's like HTTP, well, that's not H. HTTP, like SMTP for email, etc. And then there's the applications. Okay, and this is like, the thin waist that everything has to go through. And it doesn't really matter like what you use up here. These things can be swapped out and upgraded. It doesn't really matter what you use down here. They can be swapped out and upgraded. But you always need IP addresses. And so like this is awesome, right? And this is the reason that the internet is still useful, even though it was invented a long time ago and people didn't realize how we were going to use it, right? So like this is like a great structure. But now we want to swap out this middle piece that everything relies on. So that's going to cause some upheaval. What IPFS proposes is making the Merkle DAG the middle piece that you don't have any choice. You have to data is formatted in this way, which is not a big ask, but it just requires the convention of doing that. And then there's the question of now you're not going to a place. Like the routing isn't sort of the crucial thing anymore. It's how you exchange blocks with people. Like how do you ask someone for a block and how do they give it back to you? A piece of the Merkle DAG. So the exchange part. Wow, my handwriting is so bad. I'm sorry. Okay, exchange. So this is like BitTorrent is a way to exchange blocks like this. Okay, IPFS uses something very similar to BitTorrent called BitSwap, which sort of relies on the same, I'll give you stuff, you give me stuff. I'll talk about that more in a second. But then you could even use HTTP here. So like this is, I didn't line them up perfectly, but you could, there exists an IPFS gateway. So there's a computer running at IPFS.io, and if you ask IPFS.io/IPFS/some hash, it will serve it to you, and you can use the regular old HTTP web to get pieces of the Merkle DAG. And that's great because the transition can be smooth, which is key, right? Because nobody's gonna if people notice that the internet is having some upheaval, then that'd be bad, right? Nobody's actually gonna agree to that. So it has to be able to happen silently, and the gateways are one great way for this to have sort of a smooth transition, which I can talk more about in a bit. But then so how you decide when to give who what block, that's this layer. There's the sort of routing layer, how you find out what other people want and how they find out what you want and how you talk to each other and start the bargaining process. So one of the ways that IPFS does that is with the DHT, a distributed hash table. There's also MDNS, so if we're all in a room together, I can just do a sweep of who else is sending signals out essentially, right? And look at the local network and see who's there. And then there's the transport that you actually use, so that's this layer. To exchange all these packets and talk about stuff. So this can be like TCP or like WebRTC or something like that, which is what the JavaScript implementation uses a lot, or like WebSockets. But you can also have things like CJDNS is a really cool thing that I'm not going to talk about, but you can have all sorts of wild stuff in here that isn't like the standard couple protocols. And what's also interesting is that you could do these things over, or I guess, well, yeah, these things could be over I2P or Tor if you wanted to like be private about who you're asking for blocks and like don't want anyone except them to know what blocks you're asking for and stuff like that. You could do these layers over these to keep that kind of thing private. It's going to be really slow as it is now, probably slower. But you could do something like that to hide your traffic, and it's like harder as it makes sense to be. Okay, and then above this, there's a new naming layer, which is sort of not explicit in this model, but like is obviously a really important problem. So like the IPFS people decided to like think about this as its own layer, and so you could use DNS. You could use IPNS, which has an extension. This is sort of like at multiple layers, but there was an idea to like have human readable names for that. It is not implemented, and like I don't know if it's going to work. But then you could also use like blockchains, like Namecoin or something.
So you seem to be drawing a whole bunch of different options here.
Yes.
How do you end up with one coherent network if everyone can choose the combination of protocols that they want to use?
Good question. Okay, so yes.
I feel like you're going to have a whole bunch of bifurcated
Yeah.
subsets of the network.
The top thing is asked again. Okay.
Can I,
Yeah.
it seems like the reason it would work is the same reason it works now, is that Merkle DAG becomes the address.
Yeah.
That's it. And so just as you have now, the destination is always knowable, the source is always irrelevant.
Yeah. So just like where's my just like you would connect to the access point via Wi-Fi and not via Bluetooth, you have to choose when you're talking to someone, how you're going to like do this parting process. So I mean the default that all the IPFS nodes use now is bit swap, which makes things easier. But if you wanted to use something else, then you would have to. Actually, you could probably.
I mean, so for example, you have the DHT bucket
Yeah.
in there as one of the ways to exchange information. But unless all of the other people in my room are also speaking DHT, I can send that request and I won't get any response. Or maybe I'll get one response from the one guy in Europe who decided to use that protocol.
Yeah. Okay, I'll talk about bit swap first as sort of an aside, because it was designed intelligently so that you could use sort of any strategy. The way that bit swap works is you have a want list and a have list, and it's just like a list of blocks. So the people that you're connected to and your peers on the network also have want lists and have lists. And if you have something on someone else's want list, you'll send it to them unless, I think the factor is like, it's not exactly this, but it's roughly if they've given you at least half as much as you've given them, then you'll still like talk to them and be nice. But if they've given you less than half of what you've given them, then you won't give them anything. And they can run whatever strategy they want. This is just like the default one. So maybe what they're doing is they're running the strategy where if anyone asks for any block that they have, they just send it. Like they're happy to be altruistic. Maybe their strategy is they're going to be really stingy and like they're only going to send stuff to people who have sent them at least that much stuff. And it doesn't actually matter to you what algorithm your other people are running. As long as you can, as long as they'll give you stuff sometimes, then you're like happy to talk to them. And if you have to like send them something first, like that's standard, that's fair. So you'll often, if one of your peers has something that you want, then you'll like actively seek out blocks that you can give them so that they'll like, give you stuff back. Similar to BitTorrent, which is where every round you send stuff to the people who were nicest to you last round. It's kind of like that. But you can have any strategy you want at these nodes, and like you don't have to do that strategy for BitTorrent. Some people, are happy to give stuff to anyone who asks, even if they haven't given them anything back. Yeah.
Does this strategy in practice now work well enough that you don't have to have some kind of token or some kind of payment mechanism in order to support the whole thing, or is it not there yet?
It does work well enough. Yes, but they're working on a payment mechanism, which I think is really exciting. So one thing that you could add to this is, it's a project called Filecoin, which is a blockchain. But something like Filecoin, it doesn't have to be Filecoin, but some strong incentive where you say like, hey, I'll give you a nickel if you give me that block. I mean, that's probably too much, but I'll give you a nickel if you give me that block. Like, that would be awesome, right? Now there's no like, sort of, oh, what have you done for me recently? You can have this like very clear sort of incentive structure, very clear like, I'm gonna send the thing that, this round I'll like fulfill the bids that are the highest or whatever, right? And furthermore, if you had a system like that, then there's actually like a really strong incentive to build infrastructure so that you can better, like so you can send people more stuff so that you can get paid more and like, get access to, like, if there's a block that's really popular, right? Or if there's a block that would be really valuable in this area, but it's not there for some reason, like there's a huge incentive to provide that block to that group because, you could get paid for it with real money.
So I see the SIA thing on your laptop there.
Oh, yeah.
Where's SIA fit into this?
So SIA solves a different problem, which is long-term storage. They have a retrieval network also.
Do they use any of these standards?
No. Which is sad, because it would be cool if they did. And there was actually, I don't remember if it was SIA, I think, no, it was storage. Storage recently announced some like IPFS bridge so that you could get storage data through IPFS. Like they're running a node on the IPFS network that lets you like retrieve stored data. But anyways, I didn't fully answer your question, which is like, what if people want to use different things?
Yeah, it just seems like all of this choice is a bad thing for performance of the network.
Yeah. You can use different things with different peers.
Sure.
And
So the optimal thing is to speak all the protocols.
well, I mean, it's not optimal if it takes a lot of work to speak all of them, right? It's optimal to speak the ones that your neighbors want to speak. And so like, currently BitSwap is what everyone uses because you can swap out custom strategies and like everyone can still sort of speak the same language even if they have different motives. But like you can totally use anything and like you can use HTTP, right? If you're a normal Go node running on some server somewhere, you're going to be getting all of your content via BitSwap. But if you are a really light web app or something, then sure, you can get it through HTTP and you don't even have to talk to anybody who speaks BitSwap because that would be a lot of work.
So a lot of what you described here sounds like it's almost exactly the same model as Freenet. I was wondering if you could compare IPFS to Freenet.
I don't know enough about Freenet to do it justice, but there are a lot of things similar to IPFS. I actually I looked into this a bit.
Freenet's been around for like 15 years or so.
Yeah.
Okay. Content addressable thing.
Yeah.
Except Freenet has as one of its core design goals anonymity, which it sounds like this very much is,
Right.
is going in the complete opposite direction of processing anonymity.
Yeah. So one of the things that I guess they didn't prioritize was having everything be private.
I mean, to use one of your examples, right, you said that BitSwap advertises a have list. right? Find an oppressive government.
Yes.
Sure, it's easy to get content in the country, but now the oppressive government can go get a list of exactly the people that have looked at this content.
Yeah, and so like actually you can solve this just inside BitSwap, where you can choose like not to advertise some of the things that you have, like as part of your strategy.
But then
But-
no one will get the content and then it doesn't work.
Yeah, exactly. You can also not advertise that you have it, and like if someone wants it, but then there's still the problem, if you say that you want this content, then you can get,
Yeah.
policed. And so that's where like the IPFS team has sort of been like, well, you can always run it over Tor or something like that, which would make you sad if you had to do that. But it's not built in, and I think that is like one of the opinionated choices that they made. But I can see why they did it, because there are so many cases where you don't need to sacrifice speed for like hiding that you're downloading google.com or like something like that. There are a lot of cases where you would want to, and so I can imagine like one of these like things down here at the exchange layer could be sort of you only connect to like nodes that you trust. Like if you have some notion of trust, and like maybe each of your friends is running a node, and you only want to like ask for content, or like you only want to really ask for what you want to them, and then everyone agrees to like ask for what everyone wants or something, so it's like sort of obfuscated. Or you will, randomly throw things into your want list and have lists that like aren't true with some probability, so that like there's no concrete proof that what you asked for is like something you actually wanted. But these are all sort of half
I
answers.
wonder if that's good enough for an oppressive government.
Right, probably not, right. The short answer is it's not built in, and you have to do extra work at those bottom layers to get that. Yeah.
So for about 4 years now, there's been standards track activity, mostly around W3C, at this interface between distributed ledgers, privacy, and identity.
I mean, distributed ledgers are almost like, they're mutually exclusive with privacy, right? Because the whole point is you're publishing everything you do.
I mean, there's Zcash, but yes.
Well, yeah, aside from zero knowledge proofs things. Well, not exactly, yes, there are trade-offs that you're talking about. My point is that after these 4 years, now we're getting in these groups to this conversation about how do you compare IPFS to data shards to whatever alternatives there are. Once you sort of take for granted that you have distributed public ledgers available as one of the tools, along with Merkle trees and all this other stuff. And yeah, it all turns into variations of standards around distributed public key infrastructure, basically. So all I'm saying is, if you're curious, I can point you to one paper that's quite recent, like within the last couple of weeks, if you keep finding, that compares these methods. And certainly not subtle by any means, just like you're saying.
Yeah, and so some other projects, I just pulled up my list because I looked into a bunch of them before deciding that I liked IPFS the best. There's also NuNet, like GNU-net, which actually seems like, really well backed by research and like a lot of smart people. It doesn't have a ton of adoption yet, but it does have this like huge focus on, they have a cool way to trade off speed and privacy, where like if you don't care about privacy, then you'll just ask whoever, right? But you can sort of demand sort of a number of hops before you get to some place. And that's like the privacy parameter. So you could go directly there and then everyone knows you're going right there. Or you could say, oh, I want to go through my friend and then go there. Kind of in a Tor-like way.
And it's still a content address system like
I
that.
don't think that was content addressed.
Because like Tor is obviously solves that problem, but
Yeah.
Tor is connection oriented, not
Yeah.
content addressed.
They have they have their own new naming system, which is sort of interesting, and I haven't looked at it for a while, but I remember it being kind of in between. But like there is an emphasis on like public keys and stuff in the names instead of other things.
I mean, it seems to me from hearing your architecture discussion that you'd get a long way if the protocol sort of allowed you to to disclaim responsibility, right? If you say, I want this, I guess that doesn't help so much on the, no, actually it does. So if you say, I want this, and then the node that you're talking to responds with information about it and its neighbors in such a way that you couldn't tell whether the node you were talking to was actually the one that had the content, then you could apply that in both directions, and now you would just know that the have and want list is a superset of the things that anyone nearby wanted.
That's a good idea. I think, so that's a good idea. I don't think they do it for this reason, but you do, for BitSwap, I think the default actually is to, for peers that you have a bad reputation with, you will sometimes add the stuff that they want to your own want list so that you can get blocks to send them so that they will be nicer to you in the future. Not with that intent, it's with the intent of getting stuff from them later. But that seems like a reasonable thing to do, and it's a good idea.
For something like that to work, everyone has to agree to do it, even if it's bad for each individual person to have extra data.
Yeah. Right. Okay. There are a lot of components here. So I don't know, what would you guys be most interested in me talking more about of these pieces, if any?
Current
Oh, yes, I did want to talk about that, thank you. Okay, so the current implementation is, all their stuff is open source on github.com/IPFS. The officially supported implementations are Go and JavaScript. They have a sizable team working on this all the time, because, what?
Who's they?
Oh, so Protocol Labs. Protocol Labs is a cool group of people who have a variety of projects. One is IPFS, another one is libp2p, which is a peer-to-peer networking stack. Also in both Go and JavaScript, and IPFS, everything that isn't the Merkle DAG is libp2p. But they built it in a modular way that you can take individual pieces and use them usefully independently. And in fact, if Ethereum 2.0 is considering using libp2p as their networking stack, so it's used more broadly than just IPFS, and they built it so that it could be. They also have multi-hashes and multi-formats, which is a cool idea where you can have self-describing hashes. So imagine if SHA-256 were broken, then the entire Merkle DAG would just fall apart, right? And that would be bad. So you'd want to switch to SHA-3. But then if you see a hash, is it a SHA-2 hash or a SHA-3 hash? You don't want to have to try everything. So the way that they do that, the way that they address that problem is they have something at the beginning which identifies which function, and then there are more pieces than this, but it's essentially which function and then the data. And they have a whole variety of systems like this for hashes, and then they also have an address format so that you can connect to someone whose address is /IP4/18123, or you could connect to someone whose address is /P2P circuit / their public key / something about WebSockets, right? And those are all sort of multi-formatted. Their other project is Filecoin, which is what's funding all of this, because Filecoin had an ICO in the time where ICOs were legal and popular, and they raised over $200 million. So that is why IPFS can exist and is a real thing, because they have money to pay people to work on it. But it's great. So even so this is it's stable enough to use. For example, I built a social network on top of IPFS, and it works. And it all runs in the browser. You run a full node in the web page, and it just works. So it's definitely stable enough to use, and has practical applications now. So that's cool. I think I'll stop talking unless people have more questions.
lot of names. And is there any questions?
Yeah.
So it seems until a critical mass is hit, this wouldn't be viable for live websites. You'd have to almost always rely on the original server hosting the data than your peers. Having wants and needs lists won't necessarily be live. It would kind of be like set it and maybe get it in a day.
Yeah, so there are two ways around that. One is, there are two questions that could be. One is, are you trying to serve the website over IPFS? Or,
It's, yes,
Yeah,
what I
okay.
initially think.
yeah. So one way that people do that is they just send you to a gateway. So your website, all the code that makes up your website has some hash. IPFS.io/IPFS/ that hash will bring up that data, and that's pretty fast. Because the gateways are well connected to the network, and as long as you have some node running in the network that has the actual files and stuff, pinned to the network, it'll make its way to the gateway, and that'll be pretty fast. There's a page, there's this really awesome tool that someone made that tells you the latency of all the public gateways that they know about. They're 40 or something. At any given time, there are 10 that are dead-ish, but it's usually for the good ones that people are widely used, it's 500 milliseconds for a random piece of content. And then for the main public gateway, it's been kind of slow because a lot of people use that one. But there's, for example, a Textile gateway. Textile is a group that's building stuff. They have a gateway. It's pretty fast. Pinata has a gateway. They're a pinning service which will pin the files for you if you don't want to have a node online all the time. Actually, all the pinning services are pretty fast gateways because that makes sense. Yeah.
So I'm thinking about an instance where if you have a website that's being served by that gateway, so let's say you have a 100 megabyte video clip, or it doesn't matter what it is, cat video. You want that to be served by peers, preferably.
Yes. So in that case, if you have your 100 megabyte cat video, what you would do is you would run an IPFS node in the browser, which you can do because there's a JavaScript implementation, and then you'd have that IPFS node be part of the network and download the data from whatever peers it happens to connect to.
And
Which
if
is
it doesn't, it would just connect to the gateway or wherever it's hosted.
you would have to decide what you wanted to do, right? Your web page could be a node, it could just be a big JavaScript file that has a node running, or your web page could directly link http://IPFS, whatever. There's also a really cool Chrome extension and Firefox extension called IPFS Companion, which will, every time you request something from any of the gateways, if you have a node running on your computer already, it will rewrite the request and send it through your node so that it gets it from the IPFS network instead of from the HTTP gateway, which is cool.
What is that called?
It's called the IPFS Companion. And so you still have to have a node running on your computer, which is easy, right? You just
Sure.
install Go, install IPFS, and then run the IPFS data. And then the companion will detect that you have the daemon running and reroute anything for the gateways through that instead, so you're being a true node, which is cool. Cool. All right.
All right, so our speaker.
Thanks. Or something. So if it's on sort of a regular basis, let me know. You can talk to me now or send me an email. And if enough people are interested, I'll try to put a group together and we can look into some, cool thing every week or two.